Let's keep working with this example problem. So I have a ball that's 10 meters above the ground. It's 1 kilogram. And we know that its potential energy at the top is 98.1 joules, and it has no kinetic energy. And let's say it drops 4 meters. And I want to figure out its kinetic energy and potential energy at this point. Well, we can kind of do it the long way and do each part separately. So the only force acting on the ball is the force of gravity, so it's the only thing that'll do work. So the work done by gravity will be 1 kilogram times 9.81 meters per second squared times 4 meters, which will give us 39.24 joules. And it's positive, and that's because the force of gravity is going down and the ball is going down. And if that's the only force acting on it, then that's the only work, and that means that also equals the net work. So that means the net work is equal to 39.24 joules. And that means that's equal to the change in kinetic energy. And we know that because work is a transfer of energy, so if gravity is transferring 39.24 joules of energy to the ball, it should gain 39.24 joules in kinetic energy. And again, where did this 39.24 joules of energy come from that gravity has? Well, it's coming from the potential energy of the ball. Okay, so then I know the change in kinetic energy is 39.24 joules. If it started out at 0 joules, then now here at 4 meters of dropping, the kinetic energy is 39.24 joules. If I wanted to find the potential energy, like I said, the potential energy, the change in the potential energy is the negative of the work done by gravity. So it's negative 39.24 joules, which means that if I started out with 98.1 and then I lost 39.24, now I have 58.86 joules. And we'll see that because the potential energy is always the negative of the work or the conservative force, and the change in kinetic energy is always equal to the positive, right? The normal amount of the work done by the conservative force. They're always going to be the negative of each other. So if I gain 39.24 joules of kinetic energy, I have to lose 39.24 joules of potential energy. I could also solve for the potential energy another way. I could say, well, the ball's dropped 4 meters, which means it's now only 6 meters above the ground. And for the ball to get to this point, right, it doesn't matter if it's dropped or I just put it there, any ball at this point will have the same amount of potential energy. So I could just figure out the amount of negative work that gravity has to do to get to that point. And to do that, or this is just a second way to do it, I could say, well, to lift it up there, right, I would need to overcome the force of gravity. So 1 kilogram times 9.1 meters per second squared times 6 meters, right? But now if I'm saying if I'm lifting the ball up to this point, well, gravity is pulling down, but it's going up. So we have to have a negative number inside here. Those two negatives will cancel out, and I'll get 58.86 joules. And you'll see that this is just saying that lifting the ball up from the ground to here 6 meters up, the ball will have the same kinetic energy as though it was at 10 meters and dropped 4 meters, right? These are two different ways of solving for it, and they'll get you the exact same thing. So the last thing we can do is we can give you the potential energy, right? And then you can tell us the height. So if I tell you that the potential energy is 40 joules, you could say, well, how much, right, if we're lifting it from the ground, how far would I have to lift it for it to gain 40 joules of kinetic energy? Which is just like saying 1 kilogram times 9.81 meters per second squared times h, right? So at what height do I have to lift it to get 40 joules? You'll see what I did here is there's two negative signs in here, like this. And I'm just kind of canceled them out and made them a positive. So if you just divide now, 40 joules divided by a kilogram times 9.81 meters per second squared, you're going to get the height, 4.1 meters.